Hello everyone, welcome back. I hope you had a great weekend. We're going to continue on here with the last part of our apportionment unit where we learned the last method that was used in our U.S. history here, and it's called the Huntington-Hill method. All right, so this is the last piece of the puzzle that we need for this unit. Now remember, the history of this was it's kind of weird, but they initially came up with Hamilton's method, which was instantly vetoed by Washington, and then it was replaced with the Jefferson method, which was used for a while, and then that was they got rid of the Jefferson method and replaced it with Webster's method, and then stopped Webster's method and went back to Hamilton's method, and then Hamilton's method, they stopped that. And the debate was always over two things, all right? And this is they've argued about this particular math problem for almost 200 years at this point. But the argument revolved around two things. One were the paradoxes, right? So the Hamilton's method created those paradoxes, such as the Alabama, the population paradox, and the new states paradox. And there were a lot of people that did not like that. Not to mention the fact that Hamilton's method was also biased towards low population states. All right. And then the other part of the argument came from the bias, obviously, which I just stated, which is some methods are biased towards large population states and some methods were biased towards low population states in determining who got those bonus representatives. All right. And the modified divisor methods also had issues with the quota rule, which no one wanted to violate. All right. So there didn't seem to be a way to find a perfect method, and it got so bad. Congress got so bad with arguing over this that after the 1920 census, they just decided not to even reapportion Congress because they couldn't agree on a method to be used. So it got so bad they finally said, you know what, we're not going to leave this up to Congress. We're going to create a committee of mathematicians, right? Mathematicians come in and save the day, and they recommended a method called the Huntington-Hill method. And after a lot of simulations and analysis and looking at how this method played out, they found that it had very, very little bias towards large population states. It still had a little bit, but very, very little. So little it was almost negligible. And it was extremely rare that it would ever violate the quota rule. And with it being a modified divisor method, they didn't have to worry about the notion of any of the paradoxes, right? So the Alabama paradox, the new states, and the population paradox are not going to happen with this method. So this was almost a perfect method if it wasn't for the slight amount of bias towards large population states. It was finally adopted in 1941. It took them 21 years, all right, to finally replace Webster's method and put this one in place. And this is the one that we have been using ever since 1941, and no one has argued about it since. So this is the one. All right, and this is what we use today. So I'm going to show you how this method works. The step-by-step is here in the purple box. So feel free to read through that. I'm not going to read all that. I'm just going to show you how one is done, and then you can ask me questions when I return. Okay, so we're going to go back to the Delaware example, and if you recall, we calculated the divisor of 21,900. So this is the same Delaware example that we've been doing throughout this packet of notes, and we got the same divisor, again, achieved by adding up the populations, taking the total, and dividing by the 41. And I'll write that down again. We needed 41 representatives, right? So if I took 897,943 divided by 41, that would give me this divisor. All right, and then I'm going to go through and I'm going to take each individual population for the counties and I'm going to divide by my divisor. All right, and I'll get my quotas. All right, so here we go. All right, so there's my quotas. They were the same exact quotas that we've calculated in every other example that we've done with this, so nothing has changed up to this point. You're going to notice here in our next column there's this thing called a lower quota. This is exactly what Hamilton and Jefferson and Webster did. They ignored the decimal part and they just wrote down the whole number parts. That's what they mean by lower quota. So we got 7, 24, and 9. And then right next to the lower quota, I'm going to write what's called, or at least what I call, an upper quota. All right, so it's just the next number up, right? So if I have a 7 here, I'm going to write an 8. If I have a 24, I'm going to write a 25. And if I have a 9, I'm going to write a 10. You'll see why in just a minute. Okay, so I have my lower quotas with their next number up written right next to them, and then this next column is a thing called the geometric mean. All right, so in between any two numbers there is a middle, right? So in between 7 and 8 there's a middle number, and the arithmetic mean is the middle number in between 7 and 8, and we recognize that as 7.5. All right, that is the arithmetic mean, the 0.5 in between any two numbers that we see here. But the geometric mean is a little bit different. And I'm not going to go into a deep dive on what the geometric mean is in terms of the middle in between two numbers, but I'll show you how we calculate it. All right, so the way that we calculate the geometric mean in between two numbers is by multiplying them first and then square rooting them. So I do 7 times 8, which would be 56, and then I do the square root of 56, and what we get is 7.4833. So the geometric middle in between 7 and 8 is 0.4833 rather than 0.5, and we'll see why that's important in just a minute. All right, we're going to do the same thing with this one. So we got 24 times 25, and then I square root. So multiply first, then square root, and you should get 24.4949. Then I'll do the same thing here. So we got 9 times 10, then square root, and you should get 9.4868. Okay. And you'll notice these are all very close to 0.5, slightly less than 0.5, but this is what's called the geometric middle in between these two numbers. Why do we care about that? Well, because what Huntington-Hill set to do, rather than rounding based on 0.5, Huntington-Hill wants us to round these lower quotas based on the geometric middles. All right, so let me give you a demonstration. Notice that my geometric mean is 0.4833. When I go back to my quota, this says 0.4111. So this decimal portion is less than the geometric mean, so we're going to stay at 7. And then we come down here, look at the quota. 0.5872 is more than 0.4949. So this one's going to round up to 25. And we do the same thing here. 0.0017 is less than 0.4868. So this one's going to stay at 9. So instead of rounding based on 0.5, which is the arithmetic mean between two numbers, we round based on the geometric mean. So if we are more than the geometric mean, we go up. If we're less than the geometric mean, we stay put. All right. Now, once we've rounded based on those numbers, we add up our apportionment, right? So 7 and 25 and 9 add up to 41, and we have apportioned enough. That's exactly what we needed. Okay, so this 7, 25, and 9 would end up becoming our final apportionment for the state of Delaware. All right, so just a recap, right? Find your divisor, find your quotas, calculate your geometric means, and then round based on those geometric means. All right, that's as simple a set of instructions as I can give you. All right, now what happens if you get to the end here and you don't get the correct number? Well, remember I told you this is a modified divisor method. You have to go and adjust the divisor and start over. All right, so it's still kind of tedious and it's still not the prettiest thing in the world, but it is the best method that we have, and we have used this for now close to 80 years. So here we go. We're going to do it again this time with the state of Rhode Island, and this is the same divisor that we came up with in all of the previous examples, and we're going to go through and calculate our quotas in the exact same way. All right, so I got my quotas. Now I'm just going to take my lower quotas, which are just the whole number parts here. So 3, 11, 5, 44, and 9. And then right next to them, I'm going to write the next number up, right? So 3 and 4, 11 and 12, 5 and 6, 44 and 45, and then 9 and 10. And essentially at the end, we're going to be choosing one of these numbers to end up as our apportionment, okay? But to figure out which one, we have to calculate the geometric mean, right? So multiply and square root, multiply and square root. You're going to do that for each set of numbers here. Okay. So I have calculated all of my geometric means here, and now I'm going to go back and I'm going to round my quotas based on this number. So rather than rounding based on 0.5, I'm going to round based on 0.4641 here. So 0.55 is greater than 0.4641, so this is going to round up to 4. 8395 is bigger than 4891, so this one rounds up to 12. Okay, 0.9061 is bigger, so this is going to round up to 6. 6527 is bigger, so this is going to round up to 45. And the last one here is less than, so it's going to stay at 9. And then I got to add these up and see how many I get. 4, 12, 6, 45, and 9 add up to be 76, and this is too many. Okay. So recall from our previous examples that Rhode Island has 75 representatives that need to be apportioned. We ended up with 76, so we're going to have to modify the divisor. As with the Webster's method, if we got too many, we need to raise the divisor. So we're going to increase the divisor up to 14,100 and see if it will work. We are going to end up with a new set of quotas as a result. We'll have to round those quotas based on our geometric means at the end. For now, let's go through and calculate our new quotas. All right, I've got my quotas here, so now I'm going to write my lower quota along with the next number up, which I call the upper quota, so lower and upper quota here. So this will be 3 and 4, 11 and 12, 'Okay, so I got all my lower and upper quotas written. Now to calculate my geometric mean, I'm going to multiply and square root. And you're probably sitting here thinking, we just did all of this, so I don't really need to recalculate all of these numbers, and you would be correct. All right, so you don't have to rewrite all this. You could literally just use this again from this table up here, because nothing changed. Okay, so now I'm going to go through and round again. So 0.5372 is larger than the 0.4641 here, so this is going to go up to 4. 78 is larger than 48, so this goes up to 12. 8786 is larger than 4772, so this is going to go up to 6. And 4945 and 4772, or I'm sorry, that should be a 4972. I wrote that down wrong. That should be 4972. Sorry about that. So 4945 and 4972. So this is less than. So this is going to stay at 44. There we go. That would have been bad. I would have rounded up. Probably got that whole thing wrong. All right, and then 90056. 0056 is less than, so this will stay at 9. And then we got to go through and add these up. And if we do, we will get 75, which is exactly what we needed. So this becomes the modified divisor that we use for the Huntington-Hill method, and this becomes my final apportionment for that problem. Okay, so again, remember the reason that they chose such a complicated method was to reduce or practically eliminate the bias towards large population states that existed with other modified divisor methods. It also avoids all of the paradoxes. You won't run into any of the paradoxes that you do with Hamilton's method, and it's extremely rare that this will violate the quota rule, but it still has the ability to do so. So it could happen, even if it's very unlikely. All right. All right, guys, that's your intro to the Huntington-Hill method. We will be doing more of these throughout the week, so give the practice problems a try. Let me know if you have questions. Have a great day.